So a while ago, a YouTuber known as SGMHRP released this video. Now you see that pendulum that's spinning like crazy? She used that pendulum to chain ground pounds together to gain height. Now, I'll explain more about how that works in a future video. But for now, the reason I'm bringing up this video is for the description. You see, SGMHRP mentions that tasking this strat would have been too tedious to deal with manually, and so she automatically generated the entire sequence of inputs. So what piqued my interest was the fact that she automated making the pendulum go crazy. You see, we've known for years how to manipulate pendulums into spinning really fast like that, which is called pendulum manipulation. And it basically involves making dust on certain frames to manipulate RNG in a certain way, which I'll cover in more depth in a bit. But unlike SGMHRP, every time I tasked pendulum manipulation, I was entering the inputs manually. Well, I did make a program to tell me what frames to make dust on, but then I had to manually enter the inputs for those dust frames, and so it was still a pretty slow process. So when SGMHRP said this whole process could be automated, that intrigued me, because it meant I could manipulate a pendulum as much as I wanted with no real effort. And so that got me wondering, if we just manipulated a pendulum to spin faster and faster forever, then what would happen? Would the pendulum break? Would the pendulum reach a maximum speed? Would the pendulum crash the whole game? Well, to understand what would happen, we need to go over some basics. So firstly, Tick-Tock Clock actually has 4 different settings, and which setting you get depends on where the minute hand is when you enter the painting. Specifically, there are 4 different sections where the minute hand can be, and so let's briefly go over each one. If you enter when the minute hand is near 12, then all the clock parts will be still. If you enter when the minute hand is near 3, then all the clock parts will be slow. If you enter when the minute hand is near 6, then all the clock parts will be random. And if you enter when the minute hand is near 9, then all the clock parts will be fast. Since our goal is to manipulate a pendulum, we actually have to enter Tick-Tock Clock on the random setting. And that's because on all the other settings, the pendulum is on a fixed course that we can never change. On the still setting, it stays still forever. On the slow setting, it just does the same 2 slow swings back and forth forever. And on the fast setting, it just does the same 2 fast swings back and forth forever. But on the random setting, it sometimes does a slow swing and sometimes does a fast swing, depending on RNG. So it's only on the random setting that the pendulum is on a dynamic course that we can control, and that's why we can manipulate what it does. And so for the rest of the video, you can assume that I'm only talking about the pendulum on the random setting. So now let's talk about how the pendulum works. The pendulum is an object, and each object is stored in a chunk of memory that looks like this. So what you see here is everything that makes up the pendulum's current state. Now, most of this information is variables that all objects have in common. For example, all objects store their position here, their speeds here, and their angles here. And to clarify these angle variables, pitch, yaw, and roll refer to the object's angles around the 3 rotational axes, as you can see here. But anyway, the object struct also allocates some space for object-specific variables, which are variables that are unique to a certain kind of object. For example, a pendulum has 6 object-specific variables, which are angular acceleration sign, angle, angular velocity, angular acceleration magnitude, pause timer, and sound timer. So here are the names of the 6 variables, and they're currently in the order that they appear in memory. But we don't care about this order, so I'm going to rearrange them into a better order. Also, we're going to remove the word angular from them because I don't feel like saying that every time. So just know that when I refer to a pendulum's velocity and acceleration, I'm really referring to its angular velocity and angular acceleration. Finally, we don't care about the sound timer because that doesn't affect the pendulum's movement at all. So now let's discuss these variables. For each variable, I'll show it on screen as I talk about it. And note that negative numbers are prefixed with an M instead of a minus sign, because that's just the way SM64 prints numbers on screen. So, the angle variable controls the orientation of the pendulum. For example, angle 0 means that the pendulum is pointing straight down. A negative angle means that the pendulum is pointing to the left of angle 0, at least from this view, and the more negative the angle, the farther the pendulum is to the left. Similarly, a positive angle means that the pendulum is pointing to the right of angle 0, and the more positive the angle, the farther the pendulum is to the right. Now you might be wondering what the units are for these angle values. Well, it's not degrees or radians, but actually a different unit that we usually just call angle units. In this system, a full rotation around a circle is 65,536 angle units. So half a rotation is 32,768 angle units, and a quarter rotation is 16,384 angle units. Separately, it'll be useful to talk about pendulum swings. We'll define a pendulum swing as one continuous movement of the pendulum. So whenever the pendulum comes to a stop, like it does on the far left and far right, then that's when one swing ends and the next swing begins. And that applies even if the pendulum only stops for one frame. So that means going from all the way left to all the way right is one swing, and then going from all the way right to all the way left is another swing. So now going back to the angle variable, we can see that during a swing, the pendulum's angle will either go from very negative to very positive if the pendulum is swinging to the right, or go from very positive to very negative if the pendulum is swinging to the left. Now let's move on to velocity. The velocity variable controls how much the angle changes by each frame. So a positive velocity means that the angle is increasing, which happens during a swing to the right, and a negative velocity means that the angle is decreasing, which happens during a swing to the left. Additionally, the velocity reaches its most positive value midway through a swing to the right, and it reaches its most negative value midway through a swing to the left, because those are the times when the pendulum is swinging the fastest. Finally, a velocity of 0 means that the angle isn't changing at all, and this happens whenever the pendulum reaches the far left or far right and comes to a stop momentarily. Now let's move on to acceleration. So there are actually two variables related to acceleration, which are acceleration sign and acceleration magnitude. Now you may know from math that for any number, that number has a sign and a magnitude. The sign is either +1 or -1, depending on whether the number is positive or negative, and the magnitude is the absolute value of the number. So multiplying the sign and magnitude together equals the original number. So here, we can actually think of the pendulum as having another variable just called acceleration, which is equal to the product of acceleration sign and acceleration magnitude, because that's exactly what the code does. It multiplies those two variables together to compute the acceleration, and then increases velocity by that amount. In other words, acceleration controls how much the velocity changes by each frame. So acceleration sign controls whether the velocity is increasing or decreasing, and acceleration magnitude controls how big those increases and decreases in velocity are. But now let's talk about the two acceleration variables individually. So the acceleration sign is always either +1 or -1. It gets set to +1 when the pendulum passes angle 0 going left, and it gets set to -1 when the pendulum passes angle 0 going right. So it'll always be +1 on the left side and -1 on the right side. This means the pendulum will always be accelerating towards angle 0. Another way of thinking about this is that if the pendulum is swinging away from angle 0, then it'll be slowing down, and if it's swinging towards angle 0, then it'll be speeding up. And then the acceleration magnitude is always either 13 or 42. Specifically, before every swing, the acceleration magnitude is randomly assigned to be either 13 or 42, with there being a 2/3 chance of 13 and a 1/3 chance of 42. So every pendulum swing has a constant acceleration magnitude throughout the whole swing. If the swing has acceleration magnitude 13, then we call it a slow swing because the pendulum's accelerating slowly, and if the swing has acceleration magnitude 42, then we call it a fast swing because the pendulum's accelerating quickly. And finally, let's talk about the pause timer variable. This variable controls whether the pendulum pauses between swings and by how much. Specifically, before every swing, there's a 50% chance the pause timer will become a random positive integer between 5 and 34, meaning the pendulum will pause for that many frames, and a 50% chance the pause timer will stay 0, meaning the pendulum won't pause at all. The way it's implemented is that if the pause timer is positive on a frame, then on that frame, the pause timer decreases by 1 while the pendulum stays still. For example, if the pause timer becomes 30, then it takes 30 frames for it to decrease back down to 0, during which the pendulum is paused for those 30 frames. Now if we were to graph these variables, then they'd look like this. So the acceleration occasionally changes from one constant to another. Since acceleration controls the change in velocity, this means velocity increases and decreases linearly. And since velocity controls the change in angle, this means angle increases and decreases quadratically, though it's meant to look pretty similar to a sine wave. Finally, the pause timer will mostly stay 0, but occasionally spike and then decrease at 1 unit per frame back down to 0. And of course, the periods when the pause timer is positive represent the times when the pendulum pauses between swings, during which the other 3 variables don't change values. Now let's look at the pendulum's code. Specifically, here's a simplified version of the pendulum's update function, which is called once on every frame. We're not going to go into this code too deeply because we kinda already went over everything it does, but just to summarize it, here's where the pause timer pauses the pendulum, here's where the acceleration sign changes after the pendulum swings past angle 0, here's where the acceleration gets added onto the velocity, here's the logic for when the pendulum comes to a stop, at which point it sets the new acceleration magnitude and maybe sets the pause timer, here's where the velocity gets added onto the angle, and then there's this line of code. So what this line does is take the pendulum's angle value, converts it from a float to a signed integer, and then sets a different angle variable equal to that signed integer value. So why does it do that? Well, remember, the angle variable that we've been talking about this whole time is a pendulum-specific variable. But the pendulum also has 3 generic angle variables that are common among all objects. So what that line of code does is take the value of the pendulum-specific angle variable and copies it to one of the generic angle variables. You see, it's important to keep the generic angle variables up to date, because those are the variables that are used when the game determines what orientation to render objects at. Like, the rendering logic wouldn't want to have to check different addresses in each object to figure out its angles. That'd be annoying to keep track of. So instead, it just checks the generic angle variables that all objects have. So to recap, the pendulum-specific angle variable doesn't have any effect on its own. It's only when its value is copied over to one of the generic angle variables that the value is picked up by the rendering logic. Now, there's something else interesting about this line of code, which I kinda glossed over earlier, and that's that the value is converted from a float to a signed integer. You see, every variable in the code has a type, which indicates what possible values that variable can hold. Some common variable types are unsigned byte, which holds an integer value between 0 and 255, signed byte, which holds an integer value between -128 and 127, unsigned short and signed short, which have even bigger ranges, and unsigned integer and signed integer, which have even bigger ranges. Now you might wonder, if signed and unsigned integers have the biggest ranges, shouldn't we just always use those ones and never the others? Well, not exactly. See, it's a trade-off because those bigger ranges come at the cost of using more memory. Specifically, here's another column showing how many bytes each type uses. As you may know, a byte is a unit of memory made up of 8 bits. A bit is the smallest unit of memory as it only has 2 possible values, 0 and 1. So in a byte, there are 2 possible values for its first bit, 2 possible values for its second bit, and so on. So in total, a byte has 2 to the 8 or 256 possible bit configurations. And each bit configuration is used to represent one value that the variable can have. For example, 100 is represented with this bit configuration. Another example, 37 is represented with this bit configuration. And one more example, 255 is represented with this bit configuration. So the number of values a variable can have is the same as the number of configurations its bits can make, and that's equal to 2 to the power of the number of bits. So let's add another column for the number of bit configurations. So the unsigned byte has 2 to the 8 or 256 bit configurations, which are used to represent the numbers 0 through 255. The signed byte also has 2 to the 8 or 256 bit configurations, but these configurations are interpreted differently, and so they're used to represent the numbers -128 through 127. And then the signed integer has 2 to the 32 or about 4 billion bit configurations, which are used to represent the numbers from about -2 billion through about +2 billion. So these variable types are very useful for when you need to represent integers in your code. But now I ask you this, what if you want a variable that isn't an integer? For example, Mario's x-coordinate shouldn't be an integer, it should be something more like a real number that has a decimal component. So let's compare real numbers to the variable types we've discussed so far. Specifically, we'll do that using this graph. On this graph, the x-axis is numbers, and the y-axis is each of the variable types we discussed, plus real numbers. So for each type, there will be dots showing which numbers are representable with that type. As we're about to see, real numbers have two advantages over these other types. First, if we zoom out, we can see that real numbers have a much bigger range than these other types, since real numbers go from -infinity to +infinity. And second, if we zoom in, we can see that real numbers are much denser than these other types, since real numbers contain all decimals. So for variables like Mario's x-coordinate, it would be ideal if we had a variable type that could represent all the real numbers. But obviously, a variable type like that couldn't exist since representing all infinite real numbers would take up infinite memory. And we don't have infinite memory. So we can't represent all infinite real numbers, but we can still represent a lot of them. And that's where the float type comes into play, whose purpose is to try to represent the real numbers. But a float only has 4 bytes, meaning that it can only represent 2 to the 32 or about 4 billion possible values, because that's how many bit configurations it can make with those 4 bytes. Now, if you were the one designing floats and wanted them to be as useful as possible, which 4 billion real numbers would you pick to be representable? Well, let's consider some possibilities. Remember, for this new type to be worthwhile, we want its values to have both a big range and high density, but it seems like we can't have both. For example, if we wanted our new type to have a big range, then one idea would be to only represent every 1000th integer, so like 0, 1000, 2000, 3000, etc. Then the range would be from -2 trillion to +2 trillion, which is a much bigger range than the signed integers. But then this type isn't dense at all, like we couldn't represent the numbers 1, 2, or 3, which isn't ideal for a variable type. On the other hand, if we wanted our new type to have high density, then one idea would be to represent every multiple of a billionth, so like 0, 1 billionth, 2 billionths, 3 billionths, etc. Then our numbers would have precision down to the billionth, which is a lot better than integer precision. But by representing so many numbers so close together, we end up using up our 4 billion allotted numbers really fast, and so the range only ends up being from about -2 to +2. So we couldn't represent the numbers 3, 4, or 5, which also isn't ideal for a variable type. So you can see the issue. If we pick numbers that are spread out over a huge range, then we don't have much density. And if we pick numbers that are very dense, then we don't have much range. So when the float system was being developed, this was the problem they faced, and they came up with a pretty smart solution. Their solution for how to choose the 4 billion real numbers was to have them be more densely packed around 0, and then become less and less dense the farther out from 0 you go. Though I should clarify, the density of floats I'm showing here is not to scale. Floats are actually much more dense than this, but here I'm showing them less dense just so that you can see how the density varies from range to range. Specifically, every time you go past the power of 2, the float values become half as dense. And the float values between two powers of 2 are all equally spaced apart. So this means there are actually the same number of float values between 1 and 2 as there are between 2 and 4, and as there are between 4 and 8, and so on. Okay, now I'll show floats with their actual density. So the float system works out pretty well, because now you can represent both decimal numbers and really big numbers, just not at the same time. So smaller numbers that are used more often in practice have decimal components with pretty good precision. For example, at the number 3, the gap between consecutive floats is very tiny, coming in at around 0.00000024, so that's pretty precise. And when you need a really large number, you can have it, but your options are less precise. For example, at the number 40 million, the gap between consecutive floats is much bigger, as it's now 4. So not even every integer can be represented as a float at numbers this big. And finally, floats extend to a huge range, going all the way from negative 3.4 times 10 to the 38th to positive 3.4 times 10 to the 38th. So anyway, for the variables that we've seen so far, the pendulum's angle, velocity, and acceleration variables are all floats. The pendulum's pause timer variable is a signed integer, and the 3 generic angle variables are also all signed integers. So now going back to the pendulum code, you'll have a new appreciation for this last line. Specifically, in order to copy the value from one variable to the other, the game has to convert a float value to a signed integer value. But wait, how does that conversion work? Well, there are 3 cases. Case 1, the float value already is a valid signed integer, like -2. In this case, converting the float to a signed integer just results in the same value. So the float -2 would be converted to the signed integer -2. Case 2, the float value has a decimal component, like 3.7. In this case, converting the float to a signed integer just involves removing the decimal component. So the float 3.7 would be converted to the signed integer 3. And then case 3, the float value is outside the range of what a signed integer can handle, like 3 billion. In this case, what do you think happens? Does it go to the closest valid signed integer? No. Does it sort of wrap around to the other side? No. What actually happens on the Nintendo 64 hardware is the game crashes. And so now we know what happens when you make the pendulum swing faster and faster. Eventually, its angle would get so big in magnitude that it would exceed 2 to the 31, which means it can't be converted to a signed integer and the game would crash. So that's the mission, make the game crash using the pendulum. And just to make sure the result is accurate, we're going to be doing this on a real Nintendo 64 console, because emulators don't always crash where consoles do. So I spent a few days coding up a brute forcer to make the TAS for me, and here you can see all my code. Once the TAS was ready, I sent it to Arc Holmes to run it, because she's a community member with a very robust TASbot setup. So she started the TAS on her setup and streamed it to Twitch, which included having a timer and chat. And so now, let's discuss what went on during that TAS. So in the TAS, I enter tick-tock clock, I put the camera into a position where you can see the pendulum, and then I go into a corner and start making dust. You see, I need Mario to make dust on specific frames, and the way I do that is by inputting forwards on the control stick, which causes Mario to walk forwards and make dust on those frames. And the reason I go into the corner is because that makes it much easier to automate the inputs. To illustrate this, let's say I didn't start Mario in the corner, but instead over here. Then if I made him walk forwards every time I needed dust, he'd eventually walk into a wall and not make dust anymore, which would be a problem. In theory, I could program Mario to walk both forwards and backwards to try to stay in place, but then my brute forcer would have to simulate Mario's walking and the camera movement, and still he might drift to the side over time, which would need correcting, so that method would be a pain to program. So instead, I went with a corner. See, there's an interesting thing about corners in this game. When Mario's in a corner, like he is here, then he's actually touching 2 walls at once. First, the wall of the treadmill in front of him, and second, the wall of the steps on his left. Now there's game logic that checks if Mario's moving into a wall perpendicularly, and if so, he'll start pushing it instead of making dust, like we saw earlier. But this game logic has a flaw in it. It only does the check on the last wall that you're touching, not all of the walls that you're touching. Here, the last wall we're touching is the wall of the steps, which means Mario can only push against the wall of the steps and not the wall of the treadmill. He can walk into the wall of the treadmill as much as he wants and he'll never push it, since there's no check being done on that wall. And so that's why this corner is the ideal place to make dust. Specifically, we can make as much dust as we want while staying in the exact same place, meaning my brute forcer doesn't need to account for Mario moving around. And as I mentioned earlier, the reason we need to make dust is to manipulate RNG to control what the pendulum does. For example, let's say the pendulum just finished a swing and now it needs to randomly decide whether the next swing should be fast or slow. So what it does is invoke RNG, or random number generation. You see, RNG has two parts to it. First, there's the RNG function, which takes in a value, performs some bit logic on it, and then spits out a completely different value. Second, there's the RNG variable, which is used as the input to the RNG function and is always equal to the last output of the RNG function. Now note that RNG is perfectly deterministic in that it follows the same sequence every time. The first RNG value in the sequence is always 0, then 57,460, then 55,882, etc. And the sequence goes on for 65,114 values before repeating. So let's walk through what happens when the pendulum calls RNG. The RNG function takes in the current value of the RNG variable, does some bit logic on it, and then outputs a new value. That new value is taken on by the RNG variable so that whoever calls RNG next will get a different output. But also, the value is given to the pendulum. So the pendulum receives a random number and it uses that number to decide what to do next. Specifically, if the random number is not divisible by 3, then the pendulum will do a slow swing next. And if the random number is divisible by 3, then the pendulum will do a fast swing next. This is why there's a 2/3 chance of a slow swing and a 1/3 chance of a fast swing. Personally, I like to imagine the RNG function as the food server in a cafeteria, and all the objects that need RNG line up to get some. So currently in our line, there's a cog waiting for 2 RNG values, followed by a moving bar waiting for 1 RNG value, followed by a pendulum waiting for 2 RNG values. And on the bottom, I'm also showing on what frame each object will make those RNG calls. So when we evaluate this, the objects would get RNG values as follows. The cog gets the next 2 RNG values, then the moving bar gets the next RNG value, and then the pendulum gets the next 2 RNG values. So let's say we want the pendulum's next swing to be fast. According to this, the pendulum's going to receive RNG value 56,497, and that number will be used to decide whether the next swing will be fast or slow. Since that number is not divisible by 3, that means the pendulum would do a slow swing next, and that's not what we want. So the question is, how do we change what RNG value the pendulum gets? And the answer, as you know, is to make dust. As I've explained, when Mario walks forwards, he makes dust appear, and he can only make 1 dust per frame. But what's interesting is that when a dust is created, it calls RNG 4 times. Why 4? Well, let me explain. Here's what it looks like when Mario makes a dust. Now if you look carefully, you'll notice that the thing we commonly call a dust is actually 2 different objects, a dust ball and a dust spray. Well actually, to be really pedantic, when Mario moves, he spawns a dust spawner object, which is invisible. And then it's that dust spawner that spawns the dust ball and the dust spray. By default, those 2 dust objects would appear exactly at Mario's position, but the programmers didn't want that. They wanted the dust to look more random. And so, both dust objects are given random offsets to their X positions and random offsets to their Z positions. As you can see, the 2 different dust objects both call RNG twice, and so that's why RNG is called 4 times in total when Mario, quote, makes a dust. Okay, now that we're all certified experts on dust, let's get back to the model. Currently, we want to change what RNG value the pendulum gets. To do this, let's make dust on frame 2, which you can see because now our line of objects has a new member. Now when we evaluate who's going to get which RNG value, it's different because the dust uses up 4 RNG values. And so all the objects after the dust now receive different RNG values. So this time, the pendulum receives RNG value 30,024 to decide whether to go fast or slow. Since that number is divisible by 3, that means the pendulum will do a fast swing, which is what we want. But now let's take a look at the second RNG value that the pendulum receives. This value is used to determine whether the pause timer becomes positive, thereby causing the pendulum to pause for a bit between swings. Specifically, the pendulum will only pause if this RNG value is even, and since it's even here, that means the pendulum will pause. But guess what? At no point in the task do we want the pendulum to pause, because that's just wasting time. Instead, I always manipulate RNG so that the pendulum never pauses. So going back to our model, the dust sequence we have here is no good because it makes the pendulum pause. So let's undo all of that, and this time we'll try a different dust sequence. Specifically, we'll now make dust on frame 4 as well. Now when we evaluate the model, it's different once again, and the pendulum ends up getting these RNG values. So this time, the first RNG value is divisible by 3, meaning the pendulum will do a fast swing, and the second RNG value is odd, meaning the pendulum won't pause. So now we got what we wanted. And this is basically the process that my brute forcer does. So I tell it whether to find a fast swing with no pause or a slow swing with no pause, then it'll create a dust sequence, calculate what the pendulum does for that dust sequence, and then check whether that meets the criteria that I specified. If the check fails, then the brute forcer moves on to the next dust sequence and tries again. So it repeats this until it finds a solution, and then that solution is added onto the task. And that was all just for one swing. In reality, this process gets repeated for every swing in the task, making sure that every swing is the exact kind of swing that we want. But now the question is, what kind of swings do we want in the task? Do we want a lot of fast swings, a lot of slow swings, or maybe some combination of the two? Well, what kind of swings we want is actually going to depend on how far into the pendulum manipulation we are. In fact, there are 3 different phases of the pendulum manipulation, and right now we're on phase 1. So the better question is, what kind of swings do we want during phase 1? To answer that, we need to do some analysis. But the thing is, analyzing the real pendulum is a bit difficult since its numbers are so big. So instead, we're going to be looking at a much simpler pendulum, which I call the Mini Pendulum. The Mini Pendulum is a fake testing pendulum that I created, and it has the same logic as the real pendulum, but with one major change. Instead of having acceleration magnitudes 13 and 42, it instead has acceleration magnitudes 2 and 3. These numbers are much smaller, so it'll be easier to visualize what's going on. Additionally, we'll continue to say that the smaller acceleration magnitude of 2 is a slow swing, and the bigger acceleration magnitude of 3 is a fast swing. So to recap, we're now going to look at the behavior of this mini pendulum because its small numbers make it easier to analyze, while at the same time it exhibits properties that we see in the real pendulum. Now remember earlier when we saw graphs of the pendulum's variables? Well, here's a snapshot of the graph that showed the pendulum's angle over time. We're going to be doing our analysis on a graph like this, but with 2 modifications. First, we're going to turn the whole thing 90 degrees, so that angle is on the x-axis and time is on the y-axis. I find this way more intuitive because now the pendulum swinging left or right directly corresponds to the curve moving left or right. And second, we're not going to use a smooth curve, but instead a series of arrows, where each arrow represents a single frame of the pendulum moving. So, let's clear all of that, and now we can start our analysis of the mini pendulum. Specifically, let's say our mini pendulum starts at angle -11 and has velocity 0, meaning it's about to start a new swing. And this swing will have acceleration magnitude 2, meaning it's a slow swing. So the pendulum would go like this. It'll swing with velocity 2 for a frame, then velocity 4 for a frame, then velocity 6 for a frame. So notice that its velocity started at 0 and then increased by 2 each frame, going from 0 to 2 to 4 to 6. And the reason it increased by 2 is because 2 is the acceleration magnitude. But once the pendulum goes past angle 0, then the acceleration sign switches from +1 to -1, and so the velocity starts decreasing by 2 each frame. So next it'll swing with velocity 4 for a frame, then velocity 2 for a frame, then velocity 0 for a frame. Now, I'm not going to draw an arrow with 0 velocity because it would have 0 length. But also, it's debatable whether that frame should be included in this swing, the next swing, or neither. So for this demonstration, frames with 0 velocity are just not going to be considered part of any swing, and will be completely omitted. So anyway, this is what a typical swing looks like, and all the info I explained earlier about the pendulum variables still applies, so let's go through the variables now. The pendulum's angle is represented by the points that the arrows land on. The angle changes quadratically as it increases at an increasing rate during the first half of the swing, and then increases at a decreasing rate during the second half of the swing. The pendulum's velocity is represented by the lengths of the arrows. So the velocity increases linearly during the first half of the swing and decreases linearly during the second half of the swing. And the pendulum's acceleration is represented by the differences between the arrow lengths. So the acceleration is a constant during the first half of the swing, and then is the negation of that constant during the second half of the swing. So this graph displays all 3 pendulum variables in a nice way. And you better get used to this graph because we're going to be using variations of it throughout the rest of the video. Now in math, there's a property of sine waves called the amplitude, which is the absolute value at the peaks and troughs of the wave. Note that a normal sine wave has just one amplitude. For example, a sine wave with amplitude 5 will go up to 5, then down to -5, then up to 5 again, and so on. So it'll always turn back around at an absolute value of 5. Now our graph with the arrows is like a sine wave rotated 90 degrees. So the amplitudes here are the values at the far left and far right of a row of arrows, and represent what angle the pendulum stops at between 2 swings. If you notice, we started at angle -11 and ended at angle 7, which are different amplitudes. That's an important observation. Like, there's no rule that a pendulum swing has to end at the same amplitude that it started at, so in practice, the starting and ending amplitudes are almost always different. Now let's look at the next swing, which will be placed on the next row. And remember, before every swing, the pendulum randomly chooses whether the next swing will be fast or slow. The last swing was slow with acceleration magnitude 2, and so now let's say it chooses slow again. So the swing would look like this. It'll swing with velocity 2 for a frame, then 4, then 6, then 4, then 2. Now these velocities are actually negative, but that aspect is captured by the direction of the arrows, and so the numbers on the arrows will purely represent the magnitude of the velocity. But just for simplicity, I'll still refer to these magnitudes as the velocity, since distinguishing between positive and negative velocities isn't going to be too important here. But anyway, you may have noticed something interesting. After those 2 swings, we're right back where we started. And that makes sense because the second swing is basically just doing what the first swing did, but in reverse at every step. And this property also holds true for fast swings. A fast swing with acceleration magnitude 3 would look like this. It goes 3, 6, 9, 6, 3. And then if we did another fast swing, it would go 3, 6, 9, 6, 3. And just to clarify my notation, blue arrows mean that the swing is slow, and red arrows mean that the swing is fast. But anyway, the conclusion is that doing the same kind of swing twice in a row results in ending up back where we started, which applies to 2 slow swings in a row and 2 fast swings in a row. So if we want the pendulum to make progress towards something, like say spinning really fast, then we can rule out doing the same kind of swing twice in a row, since that won't get us anywhere. Instead, what we can do is alternate between fast and slow swings. Alternating like this allows the pendulum to swing to a different amplitude each time, as well as go through different intermediate angles during the swing. And so phase 1 is pretty simple. We just alternate between fast and slow swings. Specifically, you can see that the pendulum does a fast swing to the left, then a slow swing to the right, then a fast swing to the left, then a slow swing to the right, etc. We do this for 8 minutes and then something pretty interesting happens. As I mentioned, by alternating between fast and slow swings, the pendulum goes through different intermediate angles during each swing. So it should be no surprise that it eventually goes through angle 0. Now remember how a typical swing works. Before the pendulum passes angle 0, it speeds up, and after it passes angle 0, it slows down. So the question is, what does the pendulum do when it's exactly at angle 0? And the answer is, it still speeds up. So when the pendulum reaches angle 0, it still increases velocity on that frame. It's not until the next frame that it's officially past angle 0 and starts decreasing velocity. And now that the pendulum's reached angle 0, we're officially on phase 2 of the pendulum manipulation, where all the rules change. For example, it used to be the case that doing the same kind of swing twice in a row resulted in ending up back where we started. But let's try that again here. So we just did a fast swing through angle 0, and now we're going to do another fast swing, which would look like this. It goes 3, 6, 9, 6, 3. That's pretty weird because we just did 2 fast swings in a row, but we're not back where we started. And that's the beauty of angle 0. A pendulum at angle 0 will increase its velocity regardless of which way it's swinging. So now, if we just continue doing fast swings, then each time the pendulum will swing through angle 0. This allows the pendulum to increase its velocity 1 extra time per swing, which I'll now highlight. As you can see, each swing reaches a max velocity that's 1 increment higher than the previous swing's max velocity. First it added a 6 to its velocity sequence, then a 9, then a 12, then a 15. You can think of these new velocities as a sort of speed boost that the pendulum gets every time it reaches angle 0. And because of these speed boosts, the pendulum ends its swing at a higher amplitude than it started at. And once you go through angle 0 once, it's very easy to continue going through angle 0 on every subsequent swing. Specifically, as long as we only do fast swings from now on, then it's guaranteed that we'll keep going through angle 0. The proof for that goes like this. The previous swing went through angle 0, and this next swing is identical up until angle 0, so this next swing will also go through angle 0. And that logic just keeps applying to every new swing. But note that that proof would not apply if we were to now do a slow swing, because a slow swing would not be identical to the previous swing. Consequently, there'd be no guarantee that it'd go through angle 0. Now going back to the real pendulum, you can see the exact moment when we switch from alternating between fast and slow swings to only doing fast swings. So now the pendulum will keep swinging through angle 0, get a speed boost each time, and then end the swing at a bigger amplitude than it started at. Specifically, here are the first several amplitudes that it reaches during phase 2, and you can see that they're increasing. And then here are the differences between those amplitudes. So notice that the differences themselves are also increasing. That means not only is the pendulum swinging farther each time, but how much it's swinging farther by is increasing. And then here are the differences in the differences. These ones are just a constant, so the pendulum won't be speeding up at an infinite rate, but you know, what we got is pretty good. Now note that nothing special happens when the pendulum swings a full 180 degrees or full 360 degrees. And that's because, as we talked about, the pendulum's angle is a float, and floats are certainly allowed to increase past 32,768 and 65,536 without any trouble. Floats don't overflow at those values, like some other variable types do. But it is pretty strange to see the pendulum swinging this far. So one way of thinking about these large pendulum swings is to imagine the pendulum in the middle of an infinitely long slinky. When the pendulum rotates clockwise, it moves down the slinky, and when the pendulum rotates counterclockwise, it moves up the slinky. So if the pendulum swings multiple revolutions, then it's not back where it started, but multiple revolutions away from where it was, and it'll take multiple revolutions swinging the other way to get back. Now remember, all the inputs after I entered the corner are automated, and I automated them using the following logic. Right after the pendulum starts a swing, my brute forcer iterates through all possible sequences of dust that can happen within the next second until it finds one that causes the pendulum to do the desired next swing. But under this logic, a problem eventually arose, which I'll illustrate with this timeline. So above the timeline, I'll put rectangles to represent the pendulum swings, and below the timeline, I'll put images of dust to represent when I make dust. And as I just explained, the dust frames are concentrated at the beginning of the pendulum swings. But now let's pan to the right. So as time goes on, the pendulum swings get longer, and so the time between dust frames also gets longer. But that causes an issue, because if there's 30 seconds of inactivity, then Mario falls asleep. And that's bad, because if Mario's asleep and I try inputting forwards, then he doesn't walk forwards and make dust. Instead, he just wakes up with no dust. So I came up with a simple solution to this problem, which goes as follows. If there's a long duration with no inputs, then just sprinkle in some Z presses. This breaks up the long periods of inactivity into several shorter periods of inactivity, separated by Mario crouching. So with this solution, Mario can work all day and night manipulating the pendulum without ever going to sleep. Now eventually, the pendulum spins so fast that it makes some interesting patterns. So let's watch one complete swing. Okay, so that's the start of the swing, and now it's gonna start moving faster and faster. At certain points, its velocity syncs up in just the right way for it to look like spokes on a wheel. See, that's 5 spokes, and now it's doing 4 spokes. And then a bit later, it's down to 3 spokes. I wonder how many spokes it'll do next. Well, surprise, it's back up to 5 for a second, and then we're finally down to 2, meaning it covers a whole revolution in just 2 frames. Now we're past the halfway point, so the pendulum's gonna slow down and do the spokes in reverse order. So we just did 5, and now we're doing 3 spokes again. Now who remembers what's next? If you said 4, you were right, and after 4, it does 5 again for a second, but sadly, now it's going too slow to make any more spoke formations, though it still has enough speed to do a few more revolutions. Finally, it stops, turns around, and does the whole thing again. So that's what a swing looks like when you get this far into phase 2. Now to put phase 1 and phase 2 into perspective, here's a graph of the pendulum's angle over time. So for the first 8 minutes during phase 1, it looks pretty normal. But then as soon as phase 2 starts, you can see that the amplitude dramatically increases. So if phase 2 is so good at increasing the pendulum's amplitude, you might wonder, why can't we just continue phase 2 until the game crashes? Well, I'd like to do that, but there's a problem. You see, after 15 hours, the pendulum swings so far and accrues such a big angle that float imprecision comes into play, which marks the start of phase 3. Remember, back when we talked about floats, we established that floats are more densely packed around 0 and then become less and less dense the farther out from 0 you go. Well, here's a nifty table showing the precision of floats in several different intervals, though there are actually more intervals before and after what's shown here. But anyway, on the left we have intervals shown in both exponent and decimal form, and on the right we have the gap size between consecutive floats in those intervals, shown in both exponent and decimal form. For example, between 1 and 2, floats are very densely packed, as the distance between consecutive floats is 2 to the negative 23. But farther out from 0, between 2 to the 25 and 2 to the 26, the distance between consecutive floats is 4, and that distance just keeps doubling with each interval. And that's a problem for us, because now the pendulum's angle is getting so big that it's reaching those intervals where not every integer can be represented. I'll demonstrate this using the Mini Pendulum. So first, let's look at the control case. Here we're swinging through angle 0 and getting a speed boost. Specifically, you can see that on the second swing, the speed boost gets the pendulum up to 9 velocity for a frame, which wasn't there on the previous swing. And I'll put a blue dot where the arrows land on angle 0, just so that point is easier to keep track of. So anyway, that's the control case, which should just look normal and expected since it's not introducing anything new yet. So let's put that aside so we can use it as a reference later. Now let's introduce float imprecision, but like artificial float imprecision that'll take place at much lower values than it does for real. So beyond these 2 red lines at -8 and +8, the floats will be less dense than normal, as they'll now only cover the even integers. Now when we step through what the pendulum does, we run into an issue. Specifically, on this frame, the velocity is 3, and adding 3 to the angle makes it go from 6 to 9. But uh-oh, 9 isn't a valid float in our model. So instead, we're gonna have to round the answer to either 8 or 10. Let's consider what would happen in both cases. If we end up rounding down to 8, then the next swing looks like this. And I'll put a blue dot on the same frame as before. So notice that this time, the pendulum did not get a speed boost. Specifically, it didn't get up to 9 velocity like the control case did. And that's because the blue dot that used to be on angle 0 is now on angle -1, meaning it's past angle 0, and so the pendulum slows down at that point. So let's put that aside so we can use it as a reference later, and now let's start a new one that gets back to where we were so we can see what happens the other way. So now if we end up rounding up to 10, then the next swing looks like this. And it doesn't really matter how that last arrow gets rounded, since that's not the focus here. Also, I'll put a blue dot on the same frame as before. So notice that this time it did get the speed boost. Specifically, it went up to 9 velocity just like the control case did. And that's because the blue dot that used to be on angle 0 is now on angle 1, meaning it's before angle 0, and so the pendulum still speeds up at that point. So as you can see, whether we round up or down is actually pretty important, because it determines whether the point that used to be on angle 0 will now be before or after angle 0, which in turn determines whether we still get the speed boost or not. So how do we determine which way to round? Well, when a calculation lands between two float values, there are actually a few different ways that can be used to round. These include rounding towards 0, rounding towards the positive direction, rounding towards the negative direction, and rounding towards the nearest valid float. Super Mario 64 on the Nintendo 64 uses that last one, where it rounds to the nearest valid float. However, that still doesn't tell us what happens here, because 8 and 10 are both the same distance away from 9, so neither of them is the closer one. So when this happens, it uses a tiebreaker to determine which way to round. The easiest way to think about this tiebreaker is as follows. Let's say we're in the interval where the gap between consecutive floats is 1, and our calculation ends up right between two float values. Then the one it rounds to will always be the one divisible by 2. Next example, if the gap between consecutive floats is 2 and our calculation ends up right between two values, then the one it rounds to will always be the one divisible by 4. Last example, if the gap between consecutive floats is 4 and our calculation ends up right between two values, then the one it rounds to will always be the one divisible by 8. So basically, you can take the gap size, double it, and whoever is divisible by that gets the preference when rounding. So now let's go back to the Mini Pendulum demonstration. The gap size here is 2, so we look to see who's divisible by 4. 8 is divisible by 4, and 10 is not, so we round to 8. But unfortunately, this is where the Mini Pendulum demonstration stops being useful, because it no longer mimics what the real pendulum does. So what does the real pendulum do when it encounters float imprecision and needs to round? Well, the float imprecision first starts to matter once the pendulum's angle exceeds 2 to the 25, or about 33 million. At that point, the gap between consecutive floats is 4, and so sometimes the pendulum's angle lands on a number that isn't representable by a float and it needs to round. But what does this rounding look like? And are there any patterns in it? Well, in order to have a productive discussion about this, we're gonna need to go on a little tangent about the modulo operator. Like, you know how we have operators for addition, subtraction, multiplication, and division? Well, think of the modulo operator as a fifth entry in that group. So how does the modulo operator work? Well, just like the other operators, it takes in two values as input, one on the left, one on the right, and then outputs a third value. Specifically, z is the remainder when you divide x by y. So let's say we're trying to evaluate 25 mod 8. This is basically asking what the remainder is when you divide 25 by 8. You've probably already worked it out in your head that 25 divided by 8 is 3 remainder 1. So 25 mod 8 is equal to 1 because 1 is the remainder when you divide. Another way of writing this is saying that 25 is equal to 8k plus 1 for some integer k. Then we know that 25 is composed of k groups of 8 with 1 left over. Okay, now let's take the natural numbers and put them into their mod 8 form, and I'll color them to make it easier to parse. As you can see, all the remainders are between 0 and 7, because you can't have a remainder less than 0, or a remainder as big as the number you're modding by, which is 8. Furthermore, the sequence of remainders makes a nice pattern. It goes 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, and just keeps repeating that. And that makes sense because as you add 1 to the input number, the remainder also goes up by 1. Well, unless you're adding that 1 to a number with remainder 7, in which case the remainder wraps around, going from 7 to 0. Similarly, you could subtract 1 from the input number, which would cause the remainder to go down by 1. Well, unless you're subtracting that 1 from a number with remainder 0, in which case the remainder wraps around, going from 0 to 7. And this doesn't only work for adding and subtracting 1, it works for any number, so long as you account for the wraparounds. For example, if we add 11 to a number with remainder 2, then we end up at remainder 5. That makes sense because 11 is 8 plus 3, so adding the 8 does 1 full cycle, going from 2 to 2, and then the 3 adds 3 more, going from 2 to 5. Okay, so now we're just about ready to use our new knowledge of the modulo operator to investigate the rounding. But first, let's recap the situation using this highly simplified graph, just so we're all on the same page. So the pendulum's been swinging farther and farther each swing, and so over time it reaches float intervals with less and less precision. Eventually, it reaches the interval with a gap size of 4 between each float, at which point the angle tries to become a value that isn't representable by floats and needs to be rounded. So now we're gonna focus in on this part and analyze what one of those swings looks like when it reaches that interval. The swing we're gonna analyze is a fast swing, so it has acceleration magnitude 42, and it'll be slowing down when it reaches this interval, so its velocity will be decreasing. So some of its velocities would look like this, where they decrease by 42 each frame. Now remember how I said the real pendulum's numbers would be hard to work with since they're so big? Well, this is what I was talking about, and that's why we've been using the mini pendulum this whole time. But since that won't work here, we have to resort to a second way of making the numbers more palatable, putting them into their mod 8 form, which looks like this. So notice the pattern that they make. It goes 8k, 8k plus 6, 8k plus 4, 8k plus 2, and then repeats. And that's because 42 is 5 groups of 8 and an extra 2. So in terms of the remainders on the arrows, subtracting 42 is like doing 5 full cycles and then subtracting an extra 2, which may or may not cause a wraparound. So that's why the remainders on the arrows decrease by 2 each time. But anyway, now I'm actually going to scale the arrow lengths using the value k equals 1. So the arrow lengths won't correspond to the original numbers we saw, but just a specific case of their mod 8 form, because that's much easier to work with. But don't worry, the properties we're about to see still apply to the original numbers. Next, we're going to add some grid lines. And remember, these are grid lines for the float values in the interval where the gap between consecutive floats is 4. But the numbers in this interval are really big, as they each have 8 digits, so they wouldn't really fit as labels on the grid lines. But once again, it'll be much easier to use the values in their mod 8 form, which look like this. So it goes 8k, 8k plus 4, 8k, 8k plus 4, and that just keeps repeating. Also, I'm going to color the 8k lines as green to denote that they get the preference when we round. Because remember, when the gap size is 4, the numbers divisible by 8 get the preference when rounding. And that's why we've been using mod 8 this whole time. So just to clarify, both black lines and green lines are valid floats. But if a calculation lands right between them, then we round to the green line. Now you may have noticed that the arrows are currently not on the grid, which was deliberate. That's because we're going to place the arrows onto the grid one by one to see if we notice any patterns in the rounding. Think of it like one of those games where you drag clothes onto the character, but in this case we're dragging arrows onto a grid, which I think we can all agree is much more exciting. But anyway, we actually have 2 cases to consider, because we could place the first arrow on a green line or a black line. So let's look at both cases, starting with the green line case. So the first arrow goes here and lands on a green line, which is a valid float. The second arrow goes here and lands between 2 lines, so we round to the green line. That rounding increased the angle by 2, which I'll mark. The third arrow goes here and lands on a black line, which is a valid float. And the fourth arrow goes here and lands between 2 lines, so we round to the green line. That rounding also increased the angle by 2, which I'll also mark. And now we're once again placing an 8k arrow on a green line, which is how we started. Consequently, the pattern just ends up repeating what we did already and looks like this. Now let's consider the second case where we start on a black line, and we'll use a fresh set of arrows. So the first arrow goes here and lands on a black line, which is a valid float. The second arrow goes here and lands between two lines, so we round to the green line. That rounding decreased the angle by 2, which I'll mark. The third arrow goes here and lands on a black line, which is a valid float. And the fourth arrow goes here and lands between two lines, so we round to the green line. That rounding increased the angle by 2, which I'll mark. And now interestingly, we're in an identical state to the first case, and so we know the rest of the arrows would look like this. So even though the two cases start out on different colored lines, they end up converging and then repeating the same pattern from that point on. And that pattern only rounds upwards, meaning it increases the angle from what it would have been if floats had perfect precision. So let's recap. When the pendulum first enters this interval where the gap size is 4, it could end up on a green line or a black line. We considered both cases and examined what rounding patterns occur during the next several frames. The two cases differed in the beginning as one rounded down and one rounded up, but very quickly they got into a groove where they continually rounded up instead of down. And this repeating pattern could go on for hundreds of more iterations across the interval. So the amount of rounding up way outnumbers the amount of rounding down. And that's good for us because it was the rounding up case that still got the speed boost in our earlier demonstration. And to clarify, when I say rounding up, I specifically mean rounding away from 0, because our demonstration would be symmetric with negative numbers. So the conclusion is this. When the pendulum's doing a fast swing, is slowing down, and is in the interval where the gap between floats is 4, then the swing has a bias towards rounding away from 0. Now interestingly, this same bias happens in other cases too, like with slow swings, when the pendulum is speeding up, and in intervals with bigger gap sizes. In other words, every combination of these has that same bias in its pattern. And these patterns can be more intricate than just rounding up 2 every time. For example, let's say the pendulum's doing a fast swing, is speeding up, and the gap size is 8. Then after the pendulum gets into its groove, the repeating pattern is round down 2, round up 2, round up 4, and that goes on for a while. So that means each instance of the pattern increases the angle by 4 from what it otherwise would have been if floats had perfect precision. So basically, whenever the pendulum encounters float imprecision, the net effect of its roundings will always be a movement away from 0. So, now that we know how the rounding works, I'm going to show a very simplified demonstration of the swings during phase 3. And for now, let's assume that we only do fast swings. Also, in this demonstration, I'm not going to show any numbers on the arrows or grid lines. Instead, this demonstration is more about showing the overall gist of what happens. So here are several fast swings, and for now, I'm drawing them as if floats had perfect precision. So this is basically what we saw during phase 2, when the pendulum went through angle 0 on every swing and each time got a speed boost. And just like earlier, I'm gonna put blue dots right where the arrows land on angle 0, so that those points are easier to keep track of. And now I'm gonna add a green bar right before the first arrow. This green bar will represent the current moment in time as we step through the arrows. So an arrow that the green bar has not gone through yet is still in the future, which I'll represent by making the arrow translucent. But once the green bar goes through an arrow, it means that the arrow frame happened and is now in the past, which I'll represent by making the arrow opaque. But here's the caveat. The future arrows will be drawn without any float rounding. So think of them more as idealistic predictions rather than a guarantee of what will happen. So when the green bar goes through an arrow, the arrow might change length a bit. And that's because when the arrow was in the future, it had perfect precision, but once it transitions to the past, it may have to round its result a bit due to float imprecision. And when an arrow changes length, that'll instantaneously affect the positioning of all the arrows after it. Also, the future arrows will still assume that we get the speed boost every swing unless proven otherwise when they become opaque. So, let's reset everything, and now let's let the green bar go around and see what happens. So notice that in the intervals with float imprecision, some arrows change size, because they're now rounding their results away from 0, which is the bias we talked about earlier. So arrows pointing away from 0 get longer, and arrows pointing towards 0 get shorter. The result of this is that the next blue dot, which was originally exactly at 0, is now a little before 0. And because it's before 0, that means we still get the speed boost on that frame. So far so good. But now the next blue dot looks like it's after 0, which means we would not get a speed boost there. But who knows, maybe something will change by the time we get there. So now as the green bar goes around the other side, it does the same thing. Specifically, the float rounding makes it so that arrows pointing away from 0 get longer, and arrows pointing towards 0 get shorter. And the result of this is that the next blue dot ends up before angle 0 again, and so we do get another speed boost. And this pattern keeps continuing. So to summarize, when the green bar goes into the intervals with float imprecision, it pulls the future blue dots closer. And then by the time the green bar gets to the next blue dot, the blue dot is before angle 0, and so we get another speed boost. And that's the crux of phase 3. So basically, the float imprecision messed up the perfect system we had during phase 2, where we just went through angle 0 every swing, but luckily, it messed it up in a way that's pretty much just as good, since now we still get a speed boost every swing. So now let's skip ahead to a bit later and on a slightly different graph. Like we discussed, the blue dots alternate between being on the left side of angle 0 and being on the right side of angle 0. And it's important that they switch sides every iteration so that we get the speed boost each time. But over time, one side ends up pulling the points a little harder than the other side, and so the points end up drifting to one side. So much so that they would stop crossing angle 0. And that's a problem, because then we would no longer get a speed boost. Instead, the pendulum would perpetually do the same two swings back and forth, rather than increase its amplitude. It's just like we saw during phase 1 when doing two fast swings in a row resulted in ending up right back where we started. But luckily, there's an easy fix. See, all the swings we've been doing in phase 3 have been fast swings. So the fix is to just throw in an occasional slow swing. That sort of mixes things up and gets the blue dots back on track for a while. If you're curious, here's a graph of the real pendulum's values for the blue dots. On this graph, the x-axis is time and the y-axis is angle, and then the red area is the range that the blue dots oscillate between. So as we step through time, it's important that the bottom blue dot stays below angle 0 and the top blue dot stays above angle 0. That way we get the speed boost each time. But you can see that the red area tends to drift up or down over time, and so I use the occasional slow swing to fix it, represented by the blue vertical lines. So that's the basics of phase 3, and how we're still able to make the pendulum swing faster despite the float imprecision. Interestingly, the pendulum eventually swings so fast that it covers a whole revolution in just one frame, which you can see right now. So the pendulum looks like it stops and then keeps going, but it was actually moving the whole time. It's just like when a helicopter's blades appear to be still, but in actuality, they're just moving at a rate that syncs up with the camera's frame rate. And then a bit later, the pendulum swings a little faster than 1 revolution per frame, causing it to look like the pendulum does a little mini swing. But that little mini swing wasn't a full swing, it was just part of a much longer swing. Specifically, a part where the pendulum was going a little under 1 revolution per frame, then a little over 1 revolution per frame, and then a little under 1 revolution per frame. So anyway, we're on the third and final phase of the pendulum manipulation. So how long do you think phase 3 lasts for? Maybe a day? 2 days? 3 days? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38... 39 days. That's right, we left the console on for 39 days. So shout out to R. Combs, who programmed her taskbot so well that it went 39 days without missing a single input. This wouldn't have been possible without her. And so, after 39 days of pendulum manipulation, we finally get to the end. The point where the game should crash from trying to convert a really large float value into a signed integer. But, would it crash? Were all my calculations correct? Did I create the task file just right? Did the taskbot execute every input perfectly? We're about to find out, and it crashed, exactly as planned. And then everyone celebrated in the chat. Let's see what we got here. Our Combs says it worked. Yup, And big thanks to you. Kierio04 says, Lidhoquilacooks noquid bohu kaubka. Okay, I guess that's technically a message. Notepad Bridges says, Happy New Year. I should mention, we timed it so that the crash would happen at midnight on New Year's 2022. So it did take me a while to finish making this video. Little Tooncat says, I was here, iYouTube. Huh, I guess Apple's been working on their own version of YouTube. Swagdude69 says, it did the thing. Yes it did. Mr. Noodlebear says, Poggers, Pan-In is real poggers. Yup, I'm real sassy. Okay, one more. Lemon32767 says, here's to another year of TTC research. Well, we did reduce all the remaining TikTok clock stars to 0.8 presses in 2022, so I guess thanks for the good wishes. And so now, I think it would be cool to go over some stats about the pendulum's journey. So first there was phase 1, which is before we reached angle 0. During this phase, we alternated between fast and slow swings. This phase lasted 8 minutes and consisted of 290 swings. The swings in this phase lasted around 1 to 2 seconds, depending on whether they were fast or slow. Then there was phase 2, which is when we went through angle 0 on every swing. During this phase, we always did fast swings. This phase lasted 15 hours and consisted of 1,245 swings. The swings in this phase increased in length from 1 second all the way up to 1 minute. And finally, there was phase 3, which is when we dealt with float imprecision. During this phase, we mostly did fast swings, but with the occasional slow swing to fix the drift. This phase lasted 39 days and consisted of 8,854 swings, of which only 5 were slow swings. The swings in this phase increased in length from 1 minute all the way up to 11 minutes, but with the occasional slow swing lasting up to 18 minutes. And so in total, for the whole thing, we employed various techniques. This took 39.5 days and consisted of 10,389 swings, which lasted various amounts of time. Separately, here's a graph showing the pendulum's angle throughout the entire 39 days. As we discussed earlier, the amplitude increases by more and more with each successive swing. But also, each successive swing takes longer to execute. So all in all, the amplitude ends up increasing at a linear rate. And then here are the bounds of a signed integer. So we spent the whole time increasing the amplitude towards those bounds, and once we passed the bound right here, the game crashed. Now if we change the x-axis from time to swing number, then the graph looks like this. So now it's clear that the amplitude increases at a faster rate during later swings. And that's because on this graph, the curve is quadratic. And so there you have it. That's how you crash Super Mario 64 using nothing but a pendulum. You just go into a corner, make some dust, and then 39 days later the game crashes. And so, thanks for watching.